Hello everyone. Welcome to this video in which we will be discussing about a method known as Eigenvalue method, and this method will be used to obtain the principal stresses of the stress tensor. And further we'll be seeing that the Eigenvalue method will be leading towards some particular invariants which are independent of the coordinate system. These are the stress invariants, and they are physically important also. I'll tell you why they are important. So let me just review a bit what we have done earlier. This is a state of stress. This is a plane state of stress in which we will be having sigma xy, sigma y, and the normal stress sigma x. So a Bexel state of stress is there, and we have the shear values as well. So in a 2D, our aim is to find out the principal values, the principal state of stress, and the principal values may be oriented at any orientation. Like this is my element, and this can be rotated to any particular angle to obtain the planes of principal stresses. So it will be shown later that the principal stresses has the same stress vector oriented at the same location. So we'll be seeing that. So further, it is also known that the values of the shear stresses are 0 on the principal plane. If this is rotated with respect to principal plane, then there exists only the normal stresses sigma 1, sigma 2, and there is no shear stresses on the principal plane. So this is a principal plane, this is the principal plane. There are no shear stresses on the principal plane. So we will be looking towards this in a more general way. Now you know that we have a stress vector which is equal to the stress tensor and its unit normal oriented at a particular direction. So stress vector as a whole is independent of the coordinate. It depends on the orientation of the coordinate system, the way our coordinate system is oriented. But the components of the sigma ij are independent of the coordinate system. They are kind of a magnitude. This is kind of a magnitude, and this is particular kind of directions. So magnitudes are not related to directly to the orientation. They are independent of the orientation. This is something similar like if we have a vector v, which has three components: vi, v1, v2, v3, and the magnitude of these components, let's say, is 250, 100, 50. So the dependency is only on the direction. This acts along the x, this acts along the y, and this acts along a particular z direction. But the components or the magnitude of these vectors are itself independent of the coordinate system. They does not depend upon the coordinate system. So a particular combination of these components will lead you to the stress invariants. So we will be seeing all these things. What we are going to do now. Now we'll be understanding what eigenvalue analysis is. So for the eigenvalue analysis, just in a layman term, you can understand it like this: like this is a lot of fodder. This is one kind of a lot of fodder. This is a food for the cattle of fodder, and this is a lot of fodder. So in this lot of fodder, let's say one needle is there. It's kind of lost in this fodder. So how will you obtain this needle? You can do it for yourself, but eigenvalue analysis, if you operate the eigenvalue analysis on this fodder, the eigenvalue analysis will be able to found um, found out this needle for you in the lot of this fodder. So this is what the eigenvalue analysis is in terms of layman. What does it means in terms of stresses? We know that at a certain body, at a certain point inside the body, there exist infinite number of planes. You can consider these infinite number of planes as these fodder. But there will be one plane on which the stress will be maximum and minimum. And these are the principal planes. So I am interested in knowing the principal planes and the values on this principal plane, that is the principal stresses. So this is I'll be getting this through the eigenvalue analysis. So this needle is like a principal stress. So when eigenvalue analysis operates on any stress tensor, it will give you a principal stresses. So let's see how this eigenvalue analysis is taken by. Let's say you have a general state of stress vector Ti equals to sigma ij and j. This is a general stress state. General stress state. And then you have a principal stress state Ti. For the principal stress state, you have lambda times unit vector n, and this unit vector n is n equals to delta ij and j, and this is a principal stress state. So you have two stress states, a general stress state that will be kind of this acting on this, any stress state of the stress vector Ti that will be acting on a general state of stress, and then we'll be having a principal stress state. So on the principal stress state, this Ti vector will be perpendicular to the plane. So you'll be interested in knowing that, as I said earlier, that on a particular plane Ti component varies on the plane, and it is perpendicular to the plane only when it is a principal value. So we have these two state of stress tensor for us, a general state and a principal state rotated at particular value. And remember that this lambda here is principal values. In a layman term, what this lambda is? This needle that I am going to obtain from this fodder. So I have to obtain the needle from this fodder. If you take a difference of these two, what you will be getting? You will be getting sigma ij nj minus lambda delta ij nj, that all equal to 0. Or what you can take, can separate sigma ij minus lambda delta ij nj is equal to 0. Now I know what you will be thinking now, what is delta ij? Delta ij is a Kronecker delta. Yes, delta, Kronecker delta, and delta ij resumes or obtains the value 1 when I equals to j, and delta ij is 0 when I not equal to j. Why delta ij is put here? I'll tell you why. It has been put here so that the difference from the stress from this lambda will be taken only from the normal values and not from the shear values, because when nj operates on the delta ij is 1 for the normal stresses and 0 for the shear stresses. We'll be seeing this more towards of this. Now this becomes a homogeneous system. So in this homogeneous system, Nj cannot be equal to 0. You know that Nj's are our primary values. For a non-trivial solution, the determinant of sigma ij minus lambda delta ij should be equal to 0. And this determinant delta ij minus lambda delta ij equal to 0 can be written it like this: sigma xx minus lambda sigma xy. So the lambda has been subtracted only from the normal stresses of the stress tensor. So the determinant should be equal to 0, like this we have said. This becomes our eigenvalue analysis. So this further leads to my equation. Now if you solve this, you know how to solve this. This is a simple 3x3 matrix. How to find the determinant, I hope you know that. Keep this value constant, multiply them to subtract these two. Keep the minus of this constant, then this is removed, multiply these two, and this, you know how to do this. Just take the determinant of this, and then you will be leading towards a characteristic equation. So this will finally, when you take the determinant of this, you will be having an equation. So you will be having this equation: lambda cube minus L1 lambda square plus L2 lambda minus L3. This is equal to 0. This is also known as characteristic equation. So from this equation you can obtain the eigenvalues. And what are your eigenvalues? Lambda 1, lambda 2, lambda 3. So in terms of our stress, we are talking about stresses. So you can say that lambda is equal to principal value sigma. Sigma is a principal value. Sigma 1, sigma 2, sigma 3 is a principal value. So lambda and sigma both are same. So in this equation, as you can see, there are some quantities like L1, L2 and L3. These are the part of this equation when you have solved the determinant of this equation. These quantities are: L1 is equals to sigma x plus sigma y plus sigma z, summation of all the normal stresses. L2 is equals to sigma x sigma y plus sigma y sigma z plus sigma z sigma x minus the square of the shear stresses, minus the square of the independent shear stresses xy, yz and zx. And L3 is equal to sigma x sigma y sigma z plus 2 times of xy, yz, zx shear stresses minus sigma x tau yz square minus sigma y tau zx square minus sigma z tau xy square. So these L1, L2, L3 are the coefficients of lambda square. L2 is a coefficient of lambda and L3 is an independent coefficient. So these are known as stress invariants. These are known as stress invariants. As I said, stress invariants are a combination of particular stresses, of the stress tensor. So stress invariants are L1, L2, L3. So these L1, L2, L3 are the combination of particular components of the stress tensor, and these components are independent of the orientation of the element that we have taken. That means either you will be having this state of stress or any rotated state of stress or any state of stress you will be having. These components, but on a same point, any state of stress you will be having, the combination of these components will be same. It does not depend upon the coordinate system. The combination of the L1, L2 and L3, this type of combination is same. So any orientation, this is again your element. At a particular point, if you rotate this element at different points at different planes. So these are different planes, theta 1, theta 2 to theta 3 you will be getting. So on different planes the stress tensor is different, but at a same particular point these L1, L2, L3, these particular combinations will remain same, they will not change. So one of, like for example, I have been given this state of stress. Okay, it has a particular phase. So on these phases or on these normals, we'll be having L1, L2 and L3. So for this stress tensor, we'll be having L1, L2 and L3. Let's rotate this to a principal value. Let's say this is a principal state of stress. Sigma 1, sigma 2, sigma 1, sigma 2 and a sigma 3 is also there. And there are no shear stresses on this. So for this state also, L1, L2 and L3 will remain same. This is stress invariants, and there are physical quantities they are related to it. A particular combination of L1, L2 and L3, or you can say a particular combination of L1 with respect to a hydrostatic stress. A hydrostatic stress is one particular kind of stress taken from these components only. So hydrostatic stress and deviatoric stresses, they show you a deformation of the body. So hydrostatic stress is actually also called as volumetric stresses, volume changing stresses in fact. So they preserve the volume and they uses this L1 for you. So these stress invariants are physical quantities. They represent something physical. Like for example L2 here, or not L2, L3 here, somewhere leads to a failure theory, which is typically a von Mises failure theory. So it will tell you when the failure will happen or not. So something, many of the things you study this in higher classes, that the stress invariants are physical quantities and they are somewhere very importantly related to the failure and the shape change of the body. So now we have obtained the stress invariants. Now remember that the solution of this equation will be, this is a cubic equation. This will give you lambda 1, lambda 2 and lambda 3. These are the principal values. This will be corresponding to sigma 1, sigma 2 and sigma 3. So you will be getting the principal stresses. So in this way you will be able to find the principal stresses, and I'll tell you the corresponding vectors also you can find out from this. Now let's take one simple example and understand this concept on the example and what does they mean. Let's say we have a state of stress sigma. A state of stress has been given to us. So this is the state of stress given to us, a simple state of stress, and what we will do, we will find the eigenvalues or the principal stresses, principal directions, and we will also check for the invariance. Invariance check means we will obtain these L1, L2 and L3s before the transformation, and then we will obtain the L1, L2, L3s after the principal stresses has been found from the principal stress tensor, and we will check that these stress invariants will be same. So let's first of all find the L1, L2 and L3. So the values of L1, L2 and L3 will be, L1 is 3, L2 is minus 3, L3 is minus 1. These are the stress invariants for this stress tensor. Correct? Now let's construct the characteristic equation. You have a characteristic equation like this. So you can replace lambda by sigma. Okay? In this equation you can replace lambda by sigma. So you'll be getting directly the stresses. So you will be having sigma cube minus 3 sigma square minus 3 sigma plus 1 is equal to 0. So you will be like to solve this equation. You can directly solve this equation. This is very easy. You can also put this in your calculator to solve the cubic equation, the roots that you will be getting will be sigma equals to minus 1, sigma 2 equals to 2 plus square root of 3, and sigma 3 equals to 2 minus square root of 3. These are the three roots that you have obtained. Now what you will do, you have obtained the principal stresses. Now I would like to check for the invariance. Does the invariance occur here? Now what will be the matrix for the principal stresses? Let's check out the matrix. Only principal stress exists. 2 plus square root of 3 minus 2 minus square root of 3, 0, 0. The shears on the principal planes are 0. So this is the principal state of stress at a particular point, the important values for me, and this is very easily obtained by the eigenvalue analysis. In Mohr circle, you see, compared to this, the Mohr circle analysis looks a bit cumbersome. So with this stress matrix, you can put sigma x, sigma y, sigma z. You can put sigma 1, sigma 2, sigma 3, and the shear stresses will vanish and obtain the L1, L2, L3. So if this is dash, then L1 dash, L2 dash, and L3 dash, and you will find them as these are same. So the invariance before the transformation, so my state of stress is this, and after I have obtained the principal stress, my L1, L2, and L3. So stress invariants remain always the same before and after the transformation. And what are the stress invariants? These are particular combination of the stress components of the stress tensor. So they remain the same. Now once we have checked for the invariance check we have performed. Now we have obtained what was our requirement. We have to obtain the stresses and we have to obtain their directions. So we have still not got the directions. So for the directions, so we'll be obtaining the directions. Just see this equation. See this equation: sigma ij minus lambda delta ij nj equals to 0. We'll be using this equation to obtain the directions because nj is there. So what will be our matrix now? Our matrix will be, now each of the eigenvalues are obtained like this. So for a particular eigenvalue sigma 1, you will be having three equations from this. So for sigma 1 minus lambda delta ij, that means the sigma 1 value will be subtracted from the normal stresses. So this equation will lead to these three simultaneous equations. Okay, nx, ny, and nz. This will lead to nx, where it is, nx, ny, and nz. This will lead to three simultaneous equations. So from these three simultaneous equations, you can obtain nx, ny, and nz. If somewhere the system becomes indeterminate, you can use this condition: nx square plus ny square plus nz square equal to 0. This is a constraint condition for the planes of the system, particular planes of this, sorry, not 0, 1, sorry. Nx square, ny square plus nz square equals to 1. This is a condition for the plane of the system. This is always there with this. Either use this or do not use it, that doesn't matter. But you will be always obtaining these three equations. This equation is by default will always be there with these three equations. So with these three, you will be obtaining nx, ny, and nz. The values are, so the values of this principal stress, for first principal stress, sigma 1 is, this is on the principal plane, n1 equals to nx, ny, nz, and these are the three values for you. So this n1 is basically a vector having three components: plus 1 by root 2, minus 1 by root 2, and 0. In the same way, you will be having the eigenvalue for sigma 2 also. So what is the value of sigma 2? So after solution, we will be finally obtaining the principal directions. So for sigma 1, these are the principal directions. For sigma 2, these are the principal directions. And for sigma 3, these are the principal directions. So basically these are the vectors. The directions are the sigma 1. Corresponding to sigma 1, you will be having a normal direction related to this plane. So this plane will be having 3 components. N2 will be sigma 2. Corresponding to that, we will be having 3 components. So let's I hope that you are able to understand this, how these eigenvectors are calculated. Let me just review it for you. So in the case of sigma 1, what we did, we utilized this equation, the equation that we have already have, this sigma ij minus lambda delta ij nj equals to 0. This equation we have utilized here. So this is sigma xx plus lambda. So lambda was sigma 1, that is minus 1, used here. Nx plus the shear stress ny plus nz equals to 0. We have just used this, the state of stress, and we have, like, this is state of stress, and nx, ny, nz equal to 0. Just multiply them together and you will be obtaining these 3 equations. Together with nx square, ny square and nz square equals to 1. This is a constraint condition, will always be there for you. Constraint condition will always be there with you. If you require, you can use it to obtain nx, ny, nz. Otherwise, these are 3 equations are sufficient to obtain the 3 unknowns. But since they are equal to 0, so many times you will be having difficulty in obtaining any one of the components of the this direction vector. So you can use this equation very efficiently. So after obtaining them, for sigma 1, sigma 2 and sigma 3, we will be having, for sigma 1 we will be having the unit normal vector n1. For sigma 2 we will be having unit normal vector n2, and for sigma 3 we will be having unit normal vector n3, corresponding to the 3 eigenvectors. Now we have obtained these 3 eigenvalues and eigenvectors. Now it will be important for us to determine how it looks like on the figure. How it looks like, the eigenvalues and the eigenvectors. So let's consider a 3D body. Let's consider a simple 3D body. Okay, there is a 3D body, and what was my state of stress? So this was sigma 1 1. So this is 1. Sigma y, sigma z 1, sigma z 1. I request you to put the shear values by yourself. So tau xy will be 2. Put the value and put the other values also. Complete the state of stress on this cube. Now I will be looking towards the oriented cube, that is oriented at a principal values. So let's say, so this was your original state of stress. Now what will be the rotated components of the vector? So the rotation occurred somewhat like this. So plane, and then you will be having so let's say it rotates like this. This is the same vector 1, so this is, let's say, along x. So this is x. So now on this plane, my sigma 1 acts on this plane, correct? Sigma 1 and the vector acts on this plane. So this plane is represented with n1, correct? This one is represented with n2. This is represented with n3. Okay. and along this sigma 1 will exist, along this sigma 2 will exist, along this sigma 3 will exist. And what is this n1? N1 is my vector 1 by root 2 minus 1 by root 2 and 0. And what will be the projection of this vector along the x? So if the principal state has been obtained at an angle theta p, so let's say this is theta p1 first orientation, another orientation will be along sigma 2, sigma 3. So let's say theta p1 is your principal orientation. So what will be the projection of this on the x? This will be cos theta p1. So cos theta p1 will be equal to base upon hypotenuse. So this is 1 upon square root of the components 2. So in this way, let's say we'll be obtaining the theta t. Theta p is the rotation here. In the similar way, there will be a theta p existing for sigma 2 also. This will be theta p2. And remember that whenever the orientation occurs, it occurs about certain plane. So let's say my orientation here is occurring along this sigma 3. So acting along this. So it's occurring on the plane. Which plane it is? It is occurring about plane xy only. It's occurring about plane xy. So this is my plane xy. It's occurring along that 1, 3. So in this way you can obtain theta 1, theta 2, theta 3. People don't used to do till here. Only the components if you have obtained, that's okay. But for the nature, I just wanted to tell you how these things are done. So these are the stresses and the invariants. So let me just, since this video becomes a bit heavier for you, let me just review it for you what we have done till now. So we had a principal, we have a state of stress, and on this state of stress different components exist, and we wanted to rotate this state of stress to a principal state of stress. So we have used an eigenvalue method. So with the help of eigenvalue method, we have seen the eigenvalue analysis, and through the eigenvalue analysis we have gone through using the characteristic equation. Through the characteristic equation we have lead towards the L1, L2 and L3. These were the stress invariants, and the stress invariants leads to the same values even before and after the transformation. So these are the physical components. So then we have taken one example, and we have seen the check for the invariance, and we have seen how to obtain the principal stresses and how to obtain the directions of the principal stresses, that is principal vectors or the eigenvectors. So eigenvalues and eigenvectors we have seen and how to obtain. It's also important, it's also informative when you put your vectors and everything in terms of figure. So I hope that this video would be some information, will bring you some information to you, lead you to good, and if you have any problems you can have in the comment section. Thank you for now.